We're looking at the moment of inertia of a ring. This is not a disc. This is a little thin ring like this. Okay. So if we have this ring of mass m and a radius r, what's its moment of inertia in the center? Well, as before, anything that you're trying to add up, you add up the differentials. And since moment of inertia, like gravitation, comes from a small amount of mass. So we'll just take this little bitty point right there and we'll call that dm. Well, so I equals the adding up of dm r squared, because we know our equation for I is mr squared for a mass, for a point mass. Well, we have to figure out what r squared, we've got that. Isn't that a constant? So it comes out of the integral. And what does the adding up of all the little dm's give you? M. So my moment of inertia is simply m r squared, which we already knew. And that's where that comes from. However, now I'm going to do something to go one step farther on this. Instead of making this a ring, which is this, let's make it a disk, a solid disk. And isn't a solid disk made up of a bunch of concentric rings? And all together, all of those little rings add up to the total mass of the thing. Now when I do that, let's once again, we've got I equals the summation of all the little di's, which is going to equal dm r squared. Now r is not going to be a constant anymore, is it? Because r here is only that much. So we're actually going to add those up where r is 0 to r is big R. Well, we need to figure out what our dm is, because we need m as a function of r. You remember how before we used lambda for that, where we found m as a function of x. But this is in area. So now we're going to use sigma, where sigma is defined as kilograms per meter squared, which equals big M over A, or my little dm over a little area. So now we know that dm equals sigma dA. Now here's where it gets a little weird. If I plug this in, and you're saying, hey, I'm getting close. I'm going from 0 to r of dm, which is sigma dA times r squared. That's an A, that's an r. They're not the same variables. But what does A have in it? R. So if my area equals pi r squared, then dA as a function of r, the derivative with respect to r, equals 2 pi r. So dA equals 2 pi r dr, or the circumference of a circle times a really thin width will give me a ring. That gives me the area of the ring. And if I add up all of these little rings, I get the whole thing. So I plug it in. I equals from 0 to r of sigma dA 2 pi r dr times r squared. And I'm going to add all those up. And I'm going to take out the constants. Aren't these constants here? 2 sigma pi from 0 to r of r cubed dr. This says take the antiderivative where r is the only variable. Well, what's the antiderivative of r cubed? R to the 4th, which gives me, I need a little bit more room here, I equals 2 sigma pi r to the 4th over 4. And what can I do with that again? I can always take out the constants, which gives me 1/2 sigma pi final minus initial. That's not what we expect, is it? That's not our answer that we have that we've used before. This is starting to get in your way, so let me move this over here. So now, taking what we have, can you see right here? Okay, so I equals sigma is m over the area, which is pi r squared, times pi times r to the fourth. Two of them cancel, the pi's cancel, which give me, there was a fourth there. That's a 1/2, sorry. Everybody see that? 2 divided by 4, yes? Which gives me 1/2 mr squared, which is we know to be the moment of inertia of a disk.